Megnyitottál, Gabi? Most látom a résztvevőket. 11. Hú, de megy felfelé, baszki, már 20 vannak. 22. Most megállt 31-nél.
Okay, so now let's get started. Good morning, everyone. My name is Oliver Sun, and I am an undergraduate student in Untitled Group at UCSD. I'll be co-hosting today's webinar with Matt, a graduate student in the group. So before we get started with our guest speaker, I would like to make a few announcements. First, the JCP has a special topic with regard to polariton chemistry. If you're interested in it, please make sure to check out the link here down below. Please be aware that the deadline for submission is October 16th, 2020. Also, our webinar is held every Wednesday at 9 a.m. Pacific Standard Time. Here you can see the schedule for the upcoming webinars. If you haven't registered to the series yet, please go to the link here and or click on the link in our weekly reminder email to register. Also, we have a Facebook group called Polariton Chemistry Online Community, where everyone in the field is welcome to share their recent findings, research papers, or other topics related to the field. Please join the group if you haven't done so already. Also, for this series of webinars, we have a YouTube channel called Polariton Chemistry Webinars. So if you have a schedule conflict or are in a different time zone so you cannot join the real-time webinar, or if you would like to watch some of your favorite webinars one more time, you can always go to our YouTube channel. Make sure that you have subscribed to it. In this page, I will introduce you to the mechanics of the webinar. So in the bottom of your Zoom window, you will see 3 icons. When you have a question, you can click on the raise hand button, where I will interrupt the speaker at an appropriate time so that you can ask your question real time. If you prefer your questions to be answered at the end of the webinar, you can use this Q&A function at the end of the Zoom window. So at the end of the webinar, we will get through all the questions on the Q&A panel and the speaker will address it. If we don't have enough time to address all of the questions, we will send the list of questions to the speaker, and then she will address it later. And also, we have a chat function. So if you would like to share some thoughts or some ideas throughout the talk, you can always use that. And for today's talk, we are honored to have Professor Agnes Vibok from the University of Nebraska with us. And Matt will introduce Professor Vibok to us.
Professor Vibok earned her master's and PhD in physics at Kossuth Lajos University in Debrecen, Hungary. Under the advising of Professor Istvan Meyer, she did her graduate research on electronic structure theory for intermolecular interactions. Next, she was a postdoctoral fellow at University of Bristol, working with Professor Gabriel Curti on complex absorbing potential for wave packet dynamics. Professor Vibok then did a postdoc fellowship at Joseph Fourier University with Dr. Pierre Valiron and a research fellowship at Kossuth-Lajos University, resuming development of electronic structure theory for systems of interacting molecules. She then started and continues her professorship at Kossuth-Lajos University, which has now since merged with other schools to form the University of Debrecen, her current affiliation. Professor Vibok has made significant contributions to the understanding of non-adiabatic coupling, conical intersections, and Berry phase in molecular systems. She has won a number of grants and fellowships, including Soros Foundation grants, a Young Investigator grant, and the International L'Oreal UNESCO Fellowship. Her current research interests include light-induced conical intersections and non-adiabatic molecular dynamics in the presence of classical and quantum light, from weak to strong light matter interaction. Please welcome Professor Agnes Vibok, who will talk about recent developments on quantum light-induced non-adiabaticity in molecular systems. Professor, you may now share your screen.
I would like to thank for this nice introduction, and I try to, can you see?
No, did you click the green button that says share screen and then your PDF?
Okay. Green button.
Yeah, on the bottom of your Zoom.
Okay. Can you see?
Yes, we see it now.
Is that okay? Oh, sorry. Is it fine?
Yeah, perfect.
Okay. Thank you very much. This nice introduction. And I also would like to thank for the organizers, for Hoer, UNZU, and for Wei Songs for the invitation and to give me a possibility to talk about our recent work on the light-induced nonadiabaticity in molecular system. So at the beginning of my talk, I also would like to thank for the collaborators from University of Debrecen, Gábor Halász, András Csehi, Peter Badanko, from University of Heidelberg, Lorenz Cederbaum, from Eötvös Loránd University, Budapest, Csaba Fábri, Tamás Szidorovszky, Attila Császár, and from Stockholm University, Markus Kowalewski. It's a brief overview from my talk. At the beginning, I would like to give a very short introduction about the non-adiabaticity in a molecular system, in nature, mostly nature and non-adiabaticity. And the second part will be devoted for our results. At the beginning, I will try to summarize our results on diatomic. And the second part of my talk to show our recent results in polyatomic system. So that it is well known in the non-adiabatic phenomena that the nature and non-adiabatic effect arises due to the avoided crossing or conical intersections. These conical intersections are singularities between Born-Oppenheimer potential energy surfaces. From now on, I will call them VO potential energy surfaces. In this situation, there is a strong mixing between the electronic states, the vibrational and rotational states of the molecule. It is also known that in field-free diatomic, only avoided crossing can be formed and not a conical intersection. It's a small summarization here. In the adiabatic to diabatic phenomena, we transform the non-adiabatic coupling back and forth from the potential to the momentum and back. In the diabatic representation, the strong non-adiabatic coupling is in a potential energy The potential energy in this case is a full matrix, and we can transform the non-adiabatic coupling into the momentum coupling. And in this case, the potential energy will be a diagonal form with a V plus and V minus in the diagonals. These two adiabatic potential can cross each other and form a conical intersection whenever this condition fulfilled. So the delta square plus each H12 square should be 0. So we have two criteria has to be fulfilled at the same time. And then for this, we need at least two independent vibrational degrees of freedom. And then one can be the linear coupling vector, another one is the gradient different vector. So we can say that in a first order, the degeneracy is lifted in this space, which is spanned by, we call it branching space, spanned by these two coordinates, the linear coupling vector and the gradient different vector. And then it's also known that if we have a diatomic system, we have only one vibrational coordinate. And then if the two states have the same symmetry, they never cross each other. This is the so-called non-crossing rule, published more than 100 years ago by János Neumann and Jenő Wigner. And then if the two states have different symmetry, of course, the two surfaces can cross each other, but the coupling is 0. But if we have more than 1 degrees of freedom, vibrational degrees of freedom, the potential energy can cross each other irrespective of the symmetry, and the degeneracy is lifted to first order in the space spanned by the sigma and lambda. This is the linear coupling and energy in gradient different vectors. So that it is also known that conical intersection in the natural non-adiabatic phenomena are very important in the non-adiabatic processes, because this conical intersection can serve as a very efficient funnel to transfer the population from the upper adiabatic surface to the lower one. These processes are important in many biochemical and physical processes like dissociation, proton transfer, isomerization, photosynthesis in plant, fluorescence on protein, molecular electronics, and so on. As I mentioned, in natural conical intersection situation, in field-free diatomic never formed the conical intersection, but if we apply external electric field, it can be a laser or cavity, then it is also possible to form conical intersection. You see here a diatomic system. We have one vibrational coordinate, but as the laser or the cavity can rotate the molecule, the second degree of freedom can be the rotation, and the two adiabatic surfaces can cross each other, forming a conical intersection. And this situation also, the photonic mode, the electronic, vibration, and rotational modes coupled to each other. So this is. And then what I would like to mention that in a natural non-adiabatic phenomena, there is a clear fingerprint of the conical intersection and different physical properties. In the spectra, for example. In the spectra, the signature of the conical intersection is the intensity borrowing effect. It means that transitions that are forbidden in field-free case still become accessible due to strong mixing of the electronic, vibrational, rotational, and photonic mode. And then the LICI, we called it light-induced conical intersection, gives rise to further splittings. The second is the topological properties, the Berry phase. It is also well known that if there is a conical intersection, so there is a degeneracy between two adiabatic states, then each real adiabatic electronic state changes sign when transported continuously along a closed loop, which enclosing the point of degeneracy. So this is well known, and then as a consequence of this signs change of the adiabatic electronic wave function, the Berry phase or topological phase will appear in the system. The third one in the dynamics, the ultrafast population transfer, what I mentioned, in the very in the close vicinity of the conical intersection, there is a very efficient population transfer. We can see the fingerprint also in the dissociation, the fragmentation. I will show some example later on. So from now on, I will continue with our results in a diatomic system at first, and then as I mentioned at the beginning, with the polyatomic. So that as a first example of what we studied, we put a sodium-2 molecule into the cavity. We assume one confined mode of the cavity, and we coupled the two states of the sodium molecule by a confined mode. You can see here the resonant coupling and the off-resonant coupling. And what we calculated, we calculated the field spectra of the sodium dimer molecule. So that at first we defined, this is the dressing Hamiltonian, this is the matrix of the dressing Hamiltonian. These are the resonant coupling, these are the off-resonant coupling. You see here the arrows. This is the green arrow, this is the resonant, and the purple of resonant coupling. This is the coupling, this is the cavity coupling here. This is a dipole approximation. The D1G means the transition dipole of the molecule. And then you can see here the cosine theta. Theta is the angle between the molecular line and the polarization direction of the cavity mode. So that solving this problem, this matrix eigenvalue eigenvectors problem, we could define the field dress state. And by using the field dress state, we could calculate the field dress spectra. We assume a weak probe path. Therefore, we could use the first order time-dependent perturbation theory to calculate the transition amplitude. And then from the transition amplitude, we could calculate the intensity, the spectral line intensity. And then you see here the situation. We put the molecule into the cavity. This is the ground state. This is the first excited states of the molecule. This is the ground state shifted by the photon frequency. And these are the diabatic representation. You can see the dotted line. These are the adiabatic or light-induced potential, or it's called polaritonic surfaces. And then you can see this weak and strong and ultra strong, and the two adiabatic surfaces or polaritonic surfaces move from each other. And then at ultra strong coupling regime, even the ground state modified a little bit. You see here, this is the situation, this is the vibration, this is the rotation, so real conical intersection can form. And then we studied the spectra, the absorption spectra of the system. Two things are very eye-catching in these figures. First is if we increase the G, the cavity coupling, you see that the envelope, which is one envelope at the beginning, started to divided into two parts corresponding to the lower and upper polaritonic, adiabatic polaritonic surfaces. And the other, this is the 1D model. In the 1D model, we can only mimic the light-induced avoided crossing situation. Only the vibrational mode, the vibrational coordinates is taken into account as a dynamical variable. But if we assume also the rotation as a dynamical variable, our model is a two-dimensional. We can mimic the conical intersection situation, and you see the clear fingerprint of the intensity borrowing as well in the spectra. So this is very dense peak structure. So you can see that those transitions are also available, which are forbidden in field-free situation. This is a clear fingerprint in a spectra in the nature and nonadiabatic phenomena, and we could see this fingerprint as well in the light-induced in the cavity.
Professor
well.
Vibok, we have a question.
Yes.
It's from Stefan.
Hi. Hello, can you hear me?
Yes.
Hi, I just had a question about the rotational degree of freedom that produces the conical intersection in a diatomic molecule inside the cavity. So just to make sure I understand, the supplementary degree of freedom really comes from the permanent dipole coupling between the molecule and the field, which makes the Hamiltonian not, the symmetry of the Hamiltonian is not anymore correct under rotation, right? So if the molecule is not aligned anymore in the field, with the field, it will change the energy, and this is what induces the conical intersection, right?
I cannot say. We simply need, as you remember at the beginning, I showed that two criteria have to be fulfilled at the same time. So we need two different degrees of freedom to fulfill, because we have two equations. And then in this case, we have only one because we have a vibration. But by using the rotation, because a laser can rotate the molecule, as a dynamical variable, we have a second degree of freedom. That's it only.
Yes, but the rotational degree of freedom is still present even in a bare diatomic, right? So it's really the interaction with the field that makes this degree of freedom relevant, that makes the rotation change the energy of the electronic states, inducing a conical intersection. I mean, well, you need both degrees of freedom. I understand.
Yes, yes, I need both degrees of freedom.
Okay. All right, thank you.
Okay, so
Professor Vibok, we have another question.
Okay.
From Powell.
Oh, hi Agnes. So
Hi.
I really like this this contrast between the first row and the second row, where you are showing that there is a dense intensity borrowing coming from the conical intersection. But my question would be, in a regular polyatomic that has almost crossing but really avoided crossings, wouldn't you see very similar features than what you are seeing?
Yes, Joel, thank you for your question. I hope I will have time, because in the last part of my talk, I would like to show for you real polyatomic molecules. Yeah, and I can show you, because in the polyatomic molecules, we also discuss the dress state spectra. So you will see it. Yes, okay.
So I would like you just to know, so if it's just almost crossing but avoided crossing, do you see this type of dense spectra? I guess that's the question.
I can see you that you see in the first situation, in the 1D model, we have just avoided crossing. So we mimicked the light-induced avoided crossing simulation situation, and you see that it is not so dense.
Yeah, but that's just with one dimension. But in two dimensions, without conical intersection, but almost conical intersection, do you see dense spectra like in the second row?
We haven't checked it yet.
Okay, thank you.
We just know that from our preliminary work. I will show it later, not in this within this talk, but later on maybe I can discuss it with you, that we could see a clear fingerprint of the conical intersection in the dynamics, laser-induced conical intersection in the dynamics, and the fingerprint of the light-induced avoided crossing, and they behave very differently.
Okay, so
that's what we haven't checked it yet, that situation what you mentioned. Okay, so this is I would like to go further, and then the former situation, we had only one molecule and the cavity mode in the cavity photon. Now we put some demiatoms, and then we also define the Hamiltonian, the working Hamiltonian, the molecular, the atomic, the photon field, and the interaction part, again, dipole approximation. You see here the dressing Hamiltonian. We can solve the same kind of problem as before. We can also calculate the dressed states, and with this we can calculate the spectra. And you see here this is a complex system, because we have three kind of components. We have one molecule, atoms, demiatoms, and photon. And then corresponding to this is the excited stuff. You see here the excited states of the molecule. You see here the ground state of the molecule shifted by the atomic resonant photon, and then shifted by the cavity photon. And you see these are the three diabatic states. And then we are at very low coupling, so that's the adiabatic and diabatic almost the same, but if we increased 5 times the cavity coupling, so the diabatic picture, this is the diabatic, the continuous line, and the adiabatic, the dotted, will be different. So we can say that there is an indirect coupling between the atoms, molecule, and photons, and then this leads to a coherent mixing of atomic and molecular states. And then the so-called polaritonic states can be formed, and then the signature of atomic, molecular, and photonic excitations. And then if you see the field spectra, is interesting that there is a clear atomic spectra here corresponding to this. This is the molecular spectra, but somehow is affected by the photon. You see here the green peaks. But if you go to larger cavity coupling, it's strange that if you sum up these intensity lines, you see it's around 1, and then it's around 1.3, because this 2 is almost 1, and plus this one is 0.3, so altogether is 1.3. This means that changed. Even we could change the atomic spectra. This is very interesting because in the atomic spectra, only just the outlier tones effect has been found before, but we could see the intensity borrowing. This is due to the indirect coupling by the photon field with the molecular rho vibrational spectra. So this is very interesting what we obtain. Here we put additional 4, so altogether 5 atoms, and then we could change a lot the polaritonic structure of the system. And then also you see here the fingerprint of the of this in the. So we have also 4 dark state as well, not only 3 bright, but you see the fingerprint, also the spectra. So what we also played with this system, we changed the cavity photon and also the atomic resonant frequency, and we could alter the spectra very much, and we hope that it is possible if we add additional second type of entity to the quantum system. Let's say in this case, just dummy atoms, in a microscopic cavity, the dynamics of the system and its response to light can also significantly modify it. But we haven't checked it yet. We just played with the spectra. So, but now I will show dynamical results as well. This is another molecule. This is the lithium fluoride molecule. And we have also 2 states, but this molecule has an avoided crossing, natural avoided crossing. Before we had only just two bonded structure, and then now we have a dissociative states as well. And then this is the natural avoided crossing, and we created another one with a cavity. We coupled these 2 states, and then this is the light-induced conical intersection here. You see the TDM and the nonadiabatic coupling in that region, and we discussed the dynamics. So we compare the classical and cavity situation, and also we discuss different kind of cavity situations for this system. By calculating 2 different kind of quantities. First was the time-dependent population, another is the dissociation rate, which is very interesting. You see here this figure. The white figures shows the dissociated population. And you see if we increase, we have 1D, 2D, so we used Fock state, Fock vacuum. And then if we increase the intensity, you could see that we could change the dissociation, amount of the dissociation population. And you can see that by changing it is degrees, it is suppressed. We could suppress the dissociation by the cavity, but the measure of the suppression was completely different in the 1D and 2D. And then we can see here the fingerprint of the conical intersection, because the conical intersection is more efficient in the population transfer. Therefore, the population from the upper state could go down very fastly to the ground state, and the population can dissociate from the ground state only. That's why this is a much less suppression in case of conical intersection than in the avoided crossing. This is a clear fingerprint what we also obtained for a natural situation. This is what we found also here. So that in this picture, this is not so clear. We compared different kind of quantum light, not the same Fock state, but different kind of photon numbers. And we could see if we increase the photon numbers, much less amount of the population could dissociate. But there is some, how to say, difference between the n equal 5 and n equal 10. This is the photon number. And then probably there is also important the back action effect, and then we have to go further and to see more, to investigate more stuff to understand clearly what is going on. But in the last figure on this system, it's interesting what we found. We compared the classical and the cavity situation for the dissociation, and then for in a 1D model, when we just mimic the LIAC, light-induced avoided crossing, you see it in the red curves. They are more or less the same in the classical and cavity situation, but the conical intersection situation differs a lot. You see that if we increase the cavity coupling, there is a big difference between the blue lines. This is the classical description. This is the cavity. Still, further investigation are needed to understand clearly what is going on. We think that the back action effect will be very important. So we are on that, but we also would like to somehow include the cavity loss, which is not included so far in our dynamical calculation. What we also did, we used as a control knob the phase, the Z phase for the laser for the classical results, and also the squeezing phase. We use different kind of quantum light to control the molecular nonadiabaticity, and we also found that the squeezing phase, also the displacement phase of the coherent light can be a good control knob, and then can also modify the final population on the ground state, and therefore can modify the dissociation rate. But I have no time, and then this is published, so I would like to go further. So that's at this point, I would like to show our recent results, which hasn't published yet. So so far we always coupled two electronic states in the cavity, and now we changed a little, and we have only one electronic state, and we try to couple two vibrational states within one electronic state. And then to study the nonadiabatic phenomena in molecular vibrational polaritons. So we put two HCl isotope molecule into the cavity. We have infrared cavity. And then in the first situation, we have the same molecule, 35 isotope, chlorine isotope. And in the second situation, they were different. One of them is 35, another is 37. So you see here the working Hamiltonian, like before, so I do not want to repeat again myself. These are the field-free states, the basis function and then this is the dressing Hamiltonian, and then to solve this problem, we can obtain the raw vibrational polaritonic states, and then by using this, we could draw the polaritonic. These are the vibrational polaritonic surfaces. For the different molecules, we have 3 bright states. And in the case of 2 similar molecules, we have 2 bright and 1 dark state. And you see here the conical intersection situation. It is very interesting. So we could create conical intersection even when we coupled the 2 vibrational states within 1 electronic state. So we discussed the different kind of properties of this system. We discussed the dynamics. We discussed also the spectroscopical behavior, and we discussed at first time the topological feature. Now I just would like to mention this last one. As I mentioned at the beginning of the talk, that in conical intersection situation, if we have a degeneracy in the system, the real electronic wave function, in our case now we have a real vibrational wave function, changes the sign, whether we can make a closed loop around the degeneracy point. And as a consequence of this, the appearance of the Berry phase or topological phase in the system. So that I have no time to go into the details, but these equations are known from the nature and nonadiabatic phenomena, from the topological stuff of the nature and nonadiabatic phenomena. But which is the most important, that if we have two quasi-isolated adiabatic states, then the quantization condition is this, so that this is the alpha equal, it's a line integral of the nonadiabatic coupling, which can be n times pi. So it means this is the topological phase which appear in the system, and the other way we call it Berry phase. And then if we have two states, two quasi-isolated states, adiabatic states, which are close to each other, and the third state are far, then we can calculate the Berry phase with this line integral techniques. This is the nonadiabatic coupling terms. We have to make this line integral and then to obtain the Berry phase. And then what we did, we tried to check this whole stuff which is valid in the electronic structure calculation for nonadiabatic case, for conical intersection situation, to check it in the situation of vibrational polariton. And then what we obtain, you see here. So we have two different molecules in a cavity, and plus the photon. And we had, I showed it at the beginning. So when we have two different molecules, we have 4 conical intersection. And then according to this, you see here, oh, sorry, I made you see here, this 4 conical intersection, and we circle only one. And we calculated the topological and Berry phase, and we obtained it very close to minus pi. So it's perfect agreement. The same as for the electronic structure situation. And then we also did this encircling here. This is a 2-3 conical intersection, and the result is quite close again to pi. This is it also the same. And then what we did here, still different component, different isotopes in the cavity, and we try to encircle 2 conical intersection. And we obtained here that we could calculate again with the 2-state approximation the Berry phase, either alpha 1, 2 or alpha 3, 2, but they are wrong. So they are not pi. So far from to be far, they are far being pi, because in this configuration space, the 2-state approximation doesn't work, because in this configuration state, 3 states are very close together. So we cannot distinguish between the third one. So that's why the topological results can show our that we need at least 3-state approximation in that region. And if we go further, unfortunately, I have no time to discuss the structure of the D matrix, but it is also well known in the natural nonadiabatic phenomena, the topological stuff of the natural nonadiabatic phenomena. The D matrix can show this clearly, because this is obtained by a 3-state approximation. So you can see that this is a diagonal matrix, and then you can see from the number of the -1 can give how many electronic, in our case, vibrational wave function change the sign. In our case, 2 wave function change the sign, the 1 and the 3, because we have 1, 2 and 2, 3 conical intersection and circling, but the second change back because it will change twice. So that the 3-state approximation is working very well. The 2-state doesn't work if we encircle 2, but if we encircle 1, also fine. So in the last column, you can see that we have a 2nd order degeneracy, like because we have one one dark state and two bright states, like a Renner-Terrell situation. And then, so we encircle this, and we should obtain 2 pi, and these results are very far being pi, because again, the two-state approximation doesn't work in this configuration space, in this region of the configuration space. If we go to 3-state approximation, it is fine again. So we have a diagonal matrix plus in a diagonal, none of the vibrational wave functions change the sign. So this is perfect agreement. What we obtained from topological point of view for the vibrational polaritons is a perfect agreement with we know from the electronic structure. So this is fine. And then from now on, maybe I have time to discuss our recent results on a polyatomic system. And then I can show you some interesting stuff, because this is the first system, polyatomic system, what we studied in the cavity. So our sample system was the formaldehyde molecule. So we have 4 atoms. We have 6 degrees of freedom, vibrational degrees of freedom. You see the picture in the cavity. Here we can show the branching space where the first order degeneracy is lifted, light-induced degeneracy is lifted. So it is spanned by the Q2 and Q4. We use these 2 modes because along the Q modes, the TDM changes a lot. That's why we used it. And also we use the second mode, the Q2, because the CO stretching mode change a lot when we move from the ground state to the first excited states. That was the reason why we choose this branching space. And then you see the ground state, you see the shifted ground state and excited states of the molecule, and the 2 adiabatic states or light-induced states or polaritonic states and the conical intersection. And as a first step, we calculated the field rest spectra of this system in 6D, in 2D, and in 1D. In the 6D is the 6D, all modes were accounted for. 2D, we use these 2 modes, and in a 1D, we use the Q4, because within the Q2, there were no absorption spectra. We had an absorption spectra only in the field dress case will be 0, but I made a mistake. But we used the field free spectra we calculated in 3 different situations. And you see that the red shows the exact in 6D. The 2D is a blue line, more or less similar. The structure is more or less similar, roughly similar to the exact spectra. But if you see, we also calculated the 1D is quite different. So we can say that the 1D is totally different from the other 2. But even further on, we calculated the field rest spectra of this system in 1D and in 2D. In 1D, we calculated along the Q4 mode, because the TDM, as I mentioned, it is large in this direction. And in Q4 mode, because of the symmetry, the absorption spectra 0. So in 1D, we could use only just the Q4 mode. And then the results are here. So at first, I just would like to show the Hamiltonian. As usual, we have a working Hamiltonian. You can see the dressing matrix, you can see the field rest state, and you can see that the intensity is calculated by the transition dipole. What we obtained with the first order time dependent, as usual. So these are the spectra. They are very interesting what we obtained. So we choose the different kind of coupling parameter, coupling value. This is a small coupling, larger, and then this is the largest one. And you see here the results. So 2 different kind of models were applied. We used Born-Oppenheimer we calculated the dress spectra in a Born-Oppenheimer picture and in the exact picture. Born-Oppenheimer picture means that all the nonadiabatic coupling comes from the light matter coupling is neglected. In the exact calculation, this is totally accurately accounted for. So that it means that I forget to mention at the beginning, but we use this system, this H2CO formaldehyde molecule, because in the study, the geometrical arrangement, there is no natural non-adiabatic phenomena in first order. So that everything what we can find it, just only the results of the light-induced non-adiabatic, cavity-induced non-adiabatic phenomena. This is a clear picture. So the coupling is, the non-adiabatic couplings also arises from the light matter coupling, the cavity coupling. So the blue line shows the BOA picture, and the red, the exact, where the all non-adiabatic coupling accounted for. So you see the big difference. We are in a small g value, that there is a big difference. If we increase the g, the cavity coupling, you still see the difference. So they are very different from each other. And if we see the largest coupling, you can see very interesting stuff. According to the upper and lower adiabatic states, will move from each other. And then you see that here, the peaks in the lower energy region quite the same. They are very similar. So it looks that the Born-Oppenheimer approximation is working in this area, while in the larger energy region, it fails. So it's very interesting, and we wanted to understand what is going on. And then we made an analytic model. So this is the diabatic Hamiltonian. It is known that we have adiabatic to diabatic transformation matrix with a phi. This is the adiabatic to diabatic transformation angle. And then we use the simple model. We approximated the ground state and the first excited state with a harmonic potential. And then we used the dipole TDM in this form, and we calculated, this is the ADT angle. As usual, you see it here. And it also well known that if we take the derivative of this function respect to x, we can obtain the nonadiabatic coupling. This is the nonadiabatic coupling for this model. And then at this point, I would like to reflect to the work 5 years ago of Johannes Feist and his co-worker when they used a similar model. And then they used the parameter where the Wx and Wa were the same. The delta in this model was the photonic energy in the cavity, and they used constant TDM. And they calculate the NACT, and they found that the NACT is proportional to 1/g. It means when they increase the cavity coupling, they arrive to the strong coupling limit, then they found that it looks that in 1D calculation, the Born-Oppenheimer approximation in the strong coupling limit is valid. But what we obtained, you see here, these parameters corresponding to our Q4 mode. We could calculate again the nonadiabatic coupling as a derivation respect to x. And we try to calculate of the two diabatic surfaces. This is the value. And we put it, this x value, to the nonadiabatic coupling expression. And we obtain the same. This is proportional to 1/g, exactly. But if we put here the 0 number, then it's proportional to g, just completely the other. So you see, this is the analytic formula, and what we show here, this is the numerical results. It's different from the analytical picture. These come from the numerical potential that we obtained from other group. You see here, this is the diabatic picture, and this is the black line shows the ground state shifted by the cavity frequency, and this is the first order. This is the excited states of the molecule. So this has a double well structure. Okay, this is the diabatic picture, and we calculated before this crossing point, these two crossing points, and they denoted by x0. And then if we do adiabatization, you can see the adiabatic picture. The black shows the lower adiabatic potential, the red, the upper. Okay, and then we could calculate the nonadiabatic coupling. You see here in black. So this is a bimodal structure. So we have a large nonadiabatic coupling here and here. And we started to increase the cavity coupling. And then as in our model, the the transition dipole is 0 at Q4 equals 0 at the origo of the Q4 mode. These distances are the same. So the distance between the adiabatic surfaces not affected by the cavity strength. This is very important. And then we can see that if we increase slowly the cavity coupling, the structure, somehow the nonadiabatic coupling restructuring. You see here for the first, and if we increase the coupling, you see this less peak here, and then it's started to be larger and larger at the origo here. And then it is very
Professor
strange.
Vibok, we have a question here.
Yeah.
Okay, Kai, you can speak now.
All right, thank you.
Hi.
Hi, how's it going? Nice talk. This is great. I just have a quick question just from this slide. You were saying at Q4 equals 0 that the transition dipole moment goes to 0, so that the spacing between the adiabatic state should be the frequency, the cavity frequency, correct?
Yes.
So I'm a little confused because the first three, the lower couplings, cavity matter couplings, that seems to be true, but for the last, the strongest coupling, to me it seems like that the gap has actually shrunk. No, that the gap seems smaller than
here. Do you mean here?
Yes, yes.
But you see here there is a different scale. Okay.
Ah, okay.
Check the different scale.
Yes,
exactly. Yes. I can say that these distances are always the same.
Okay.
This is the most important point of our study. So
yes.
that this is only just depend from the omega. There is no coupling strength between the distance of the two adiabatic potential. And then you see in this case that there is a very large, because they are very close together, and there is a very large nonadiabatic coupling. And now we start the result. We understood the results in the spectra. So that means that when you check it if you remember, I showed it in this picture. It's a completely different, divided into two parts, and then this is okay, and this is different. You see it here. Then when you measure the spectra from the ground state, then you the measurement from the ground state to this dress state. And these states are far from the nonadiabatic coupling. Therefore, the Born-Oppenheimer approximation works very well and matches very well with the exact. But when we are at this region, this is the large energy region, we measure the spectra to the upper adiabatic dress state, then it is exactly in that region. And therefore, the Born-Oppenheimer approximation fails. So within this study, we could show a realistic example in a polyatomic system where the BOA doesn't work independently, irrespectively from the studied coupling strengths. It doesn't work. Okay. And then we went further, and then we checked also the two-dimensional situation. And then we found with the similar algorithm that in this case, we have a conical intersection, and we could find infinite nonadiabatic coupling. So we can say that in this situation also the BOA doesn't work. And we assume that also this will be the situation in the 6-dimensional case. So that we can say that the BOA approximation can fail even for the 1D quantum dynamical treatment of this molecule, this realistic molecule, irrespective of the value of the coupling strengths. So that we think that this finding can be a complement, complements previous results claiming that the BOA can be used in the strong coupling regime when we have only one vibrational degrees of freedom taken into account. So that we hope that at least we have to be careful when we use the one-dimensional simulation and then with the BOA. And even if you remember at the first point, I showed that the one-dimensional spectra, field-free spectra, was very far from the realistic. And then the next point was the BOA approximation, which doesn't work. And the third, which is very interesting, that this model was lack of natural nonadiabatic phenomena. If there is some natural nonadiabatic phenomena, which is very abundant in a large organic molecule, even conical intersection between low-lying states, then the situation is more complex. So that we have to be very careful when we are using 1D calculation in large polyatomic systems. This is what we found, motivated by a realistic. This is not a model, but it was a realistic molecule. So and then with this is the two-dimensional stuff what we obtained. This is the again the BOA and exact. You see the differences, and then when we are a large coupling regime, that still the BOA in the small energy region, it's okay, and then for the larger energy still fails. So we see the difference. That is what we obtained, and then this is the summarization. And with this, I would like to thank for your attention.
Thank you, Professor Vibok. That's an awesome talk. So we will just give 1 more minute to see. Okay, we have a question.
Hello, Agnes. Sorry, this was a very interesting talk. I want to ask you about the case where you have n atoms or dummy atoms and one molecule and a cavity case. Can you show us in the absorption spectra where are the signature of the dark states again?
Hi, Joel. That's what we could not. I go back. Okay, that's it. So we are here. Yes. So we should here 4 dark states because we have n5 dummy atom. So that's what we could not discuss. So maybe we should do it, but at the moment we have no clear picture about this. These 4 dark states. We have only just how to say, we could see that the intensity of the atomic lines, it is very pronounced because you see the scale is also different from this. Mm-hmm. But to see here that there are not, how to say, I cannot see a pronounced, this, you know, to see the fingerprint of the dark state in the spectra, because you cannot measure that. It is not clear, so it's not. We just wanted to show and emphasize with the dummy atoms that if you see that we can change even the position of the atom. So you can.
Wait, but in this case, you see clearly 3 regions, right? In this, like in where you're pointing out, there are 3 regions in this. Okay, so molecule, atom, and but they are not really the dark states, right?
Yes, not really the dark states, not.
Okay.
Not.
But the dark states, are they really dark? Are the dark states really dark, or as a function of nuclear coordinate they change intensity in a dipole moment?
I think, Joel, I can say that that's what we would like to study with the cavity loss, that the dark states can be big, how to say, can be very important in the dynamics. But no, we cannot see so clear impact of the dark states on the spectra.
Okay, I would say that would be a manifestation of the single mode effect of the molecule. I think if you instead of atoms you put molecules, then you should see them. But I'm not fully sure about this statement.
Yes, that's it. Yeah. Yes. So what was the whole message of this work? That it is what's interesting, that the atom could communicate with the molecule with indirectly with due to the photon field, and then you could see that the intensity increased due to this vibrational spectra. So that it was interesting that we could see the intensity borrowing effect even in atom, not because it's molecule, it's okay because there are a vibrational structure, but here you don't have it. You have, before we just could see the Ultrafast effect when, because if you put the atom into the cavity, then upper and according to the lower and upper surface, the one line divided into two parts, but the sum of them was the same as the one line, and now we have more. So this comes from the molecule due to across or via the photon field. So that's it. And also we playing with the different, with omega and of the atom, and with the cavity, we could change the position. And probably this will be very interesting, but not for the sodium, because this is sodium too. We should play with this, with the dissociative molecule, and then it will be more interesting to see what happened with the dynamics. This is our plan to do this, but also to build in somehow the cavity loss also, because it can be very interesting. Not in the spectra, but if we would like to do more interesting dynamics, we should do it. We should build it in the dynamics, the description. This is our plan. But that's it.
All right, so we have another question from Professor Pingu.
Can you hear me?
Yes.
Thanks. So I just had a quick question about the light-induced conical intersection. So is the degeneracy valid at the electric dipole approximation, or it's strictly degenerate even you include all higher order multiple couplings? Thanks.
I think it's also involved in the dipole approximation, because so far we only used the dipole approximation. So that actually we did the LICI at first with laser. So we could create by laser, and then so with cavity. But as you remember, I always use dipole approximation in my when I discuss in the photon light matter coupling. I always had a dipole approximation. This is the TDM of the molecule, or sometimes atom. It depends on what kind of participants are in the cavity. But
okay, so that means it could be an avoided crossing by quadrupole coupling, for example.
Sorry, I didn't understand your question. Sorry, it could be.
So the degeneracy can be broken by, say, for example, the quadrupole coupling.
Okay, probably yes. In higher order.
Thank you.
In higher order, of course, yes.
Yeah, thank you. Yeah.
So are there any other questions? Okay, Matt, you can have the mic.
Hi, so I have a question. So you showed that using both electronic strong coupling and vibrational strong coupling, you can create light-induced conical intersections and modify the reaction dynamics. So can you comment on what situations it's better to use electronic strong coupling compared to vibrational strong coupling, and then vice versa?
Electronic strong couplings, yes, that so for the vibrational strong coupling, we just this was our first results for the HCl molecule, and then we just wanted to check the topological properties, that how to say, the performance of it in a vibrational polariton regime. So we didn't play with different kind of coupling parameters. But in the electronic strong coupling, yes, there is. If you remember that I could show, let's say here in this figure when we discuss the dynamics of the lithium fluoride molecule. So this is the natural avoided crossing, and this is the another avoided crossing or conical intersection. It depends on the 1D or 2D model are applied. Then we could show that how the dissociation amount looks like. You see that we should increase the cavity coupling. And if we increase it, we arrive to a stronger coupling regime, then we could suppress the dissociation, which was also found that the cavity, how to say, suppress the dynamics. For us, the dynamics was the dissociation rate. And then this was very impressive that in a light-induced avoided crossing case, this suppress was much stronger than the conical intersection. When we simulated the conical intersection situation, we had vibration and rotation are accounted for as a dynamical variable. Then we obtained this white interval shows the amount of the dissociated particle from the ground state. It's larger than this one, so that we can with increasing the cavity coupling, we can modify the number of the dissociated particle. We can modify the dissociation process. So that's what. But to be how to say accurate, we should include also the cavity loss. That's what we would like, and many other stuff. But yes. This was what we did for Fock vacuum. This is the simulation of the Fock vacuum. And then you can see that this kind of results were published, similar results were published at the beginning of this subject by Mukamel and Markus Kowalewski, Professor Mukamel and Markus Kowalewski, where I think they discussed the sodium iodine molecule. And then there is also one avoided crossing in the system, and they created another avoided crossing, 1D, with a cavity coupling with the cavity photon, the two states, and they found that this process, the cavity, suppress the dissociation. They obtained these results as well, but we went further, and including the rotation, we could mimic the conical intersection situation, and we could show that in conical intersection situation, this is much less, this effect. Not so impressive, and that's what we would like to see in polyatomic system. Going back to the question of Joel at the beginning, just to see if we have a system, because now it is difficult to rotate molecule in the cavity, but if we have many degrees of freedom, we need only 2 vibrations to form a branching space. We don't need include rotation. And then we can discuss the conical intersection situation, which is present in the system, of course. And then probably this will be different from when one do again 1D simulation. We hope that the conical intersection situation will change very much the picture. also in dynamics, not only in the spectra, what I showed before. But this was our first step to move to the polyatomic, and we how to say, we try to be careful because there are many effects. So you see that if the nature and non-adiabatic effects still present in the system, it's more complex. So we have to, how to say, go further step by step to understand what is going on. So this was the first step was the spectra, the dress state spectra, and probably we can do something also in a dynamical way, and then properly included the cavity loss, and then to show the difference between the 1D and 2D clearly. But it's important, you see. But in what we discussed for the vibrational polaritons, this was only just what I mentioned. This was only just a topological feature, and for that, not important the cavity coupling, the value of the cavity coupling, not because it's a topological stuff. So the wave function will change the sign. It's independent from the G.
Okay, thank you.
All right, so thank you again for Professor Vibok for this wonderful talk. And if there's no more question, I'll just share my screen and make a final announcement for our webinar series. So for the webinar series next week, we will have Professor Timur Shigai from Chalmers University of Technology. If you haven't registered for the series yet, please be sure to check out this link, and we will see you all soon next Wednesday at 9 a.m. Pacific Standard Time. And thank you again for Professor Vibok for today's talk, and hope everyone enjoyed the rest of your week. All right, bye.